All right, everyone, welcome to the 50% design review. As you know, 50% is a fairly arbitrary mark. Just kind of wanted to pick something that we're still sort of an engineering process. We're working through things. Not everything's nailed down. You know, we're building towards that 100% design review as we get towards June. And really just as the team continues to grow and work in a million different directions and hopefully all in the same direction at the same time, you know, trying to give this opportunity to really just give like a line in the sand snap of where the hardware is and where the system design is going, you know, and how all of the integrated pieces really fit together. So the goal of today is to present the end-to-end hardware design to the entire team so we know what we're working with. This was sort of the same goal at PDR. We just have a lot more to talk about now. We're not going to solve all design questions in this meeting. We probably have all had multiple hour-long Slacks about every single one of these questions probably. So really it's about clarifying where, you know, at least the people who are nominally thinking about something, where they're going, making sure that we're all thinking about everything, right? That there's no huge gaps missing. And then solicit feedback and review. We're trying to get to a product that meets our objectives. Just kind of pulling back to Edwin's big Zoom energy. Please mute your mic when you're not speaking. If I say something incorrect, this is going to be recorded. There's a lot of people on the line. Definitely unmute your mic and let me know. And then otherwise, put questions in the hardware PDR Slack channel, or I invited a few people from outside. So if you're not in the Slack group, feel free to maybe private message Edwin, who can copy them into that Slack group. I nominate Edwin to do that. And then as well, you know, if you have any questions that are sort of not worth interrupting, throw them into Slack and try and keep things threaded in that Slack channel. After the PDR, we had a lot of really good discussions that, you know, kind of eventually turned into their own channels or turned into their own work groups. So just kind of keep that going. All right, well, you guys are all here on a Sunday afternoon, morning, or, you know, if anyone from Europe is calling in late at night. So why are you here and what are we doing? So we are designing for manufacture a fully open source compliant full feature ventilator. So we are one of the few teams that said, hey, there's a lot of really interesting bag valve designs, but we need to do something more. We have the capability to do more. And let's really do that because I don't think anyone has ever tackled this problem before. And part of the reason is because it was a big problem to tackle. We're also working with partners to manufacture it now and after the pandemic. So we're not just planning to do something that's only used in the next couple months. We really want to do something that has durable value. Unfortunately, that means that we've raised the bar a little bit. And that is sort of why all of the stuff that we're doing, from requirements management to reviews to code verification, is so important. But like, let's be fully transparent. The world is learning about COVID-19 and ventilator needs assessment are uncertain. So I hear, you know, everything from, right, I think we've all started to hear things about how ventilator protocols are not really the same as they were early in the pandemic and needs are shifting. I think what has not changed is that a certain subset of patients need ventilators and a not insignificant number of countries have totally inadequate ventilator resources. Those are the ones that really can't offtake a bunch of bag valve actuators. And those are the ones that we're trying to help. So it's not everyone, it's not everything, but it's real people and real cases that we're targeting. So there is and will be a need for what we're doing, but it's never been done before. So we're going to have to answer some questions, and we're doing this as a volunteer effort, which is still kind of crazy and still kind of amazing. So thank you, everyone, and let's figure out what this means to do this as an open source volunteer effort. And thanks everyone for all the effort you've put in. And then someone is not muted, who just joined. So update where we were at PDR. So this was kind of the latest and greatest, and we thought this was pretty exciting. Edwin, how long ago was PDR?
Probably, I think about a month.
Yeah, I think it was about 4 weeks ago exactly. So in the interim, we've done the alpha integration in the top left, including GUI, which you know, GUI controls. We packaged it in an assembly. We started to ship dev hardware off to multiple continents. We've started to update on the kind of full feature ventilator, including running the full custom PCB, controlling dev hardware. We started a GUI collaboration with ICS, and oh, by the way, in the corner raised over $85,000 from grants and crowdsource funding. So just like pause to like recognize the incredible work this team has done over the last 4 weeks. I guess No, it's weird to, yeah, silently all muted. Give yourself applause. Cool. So where are we going? We're planning to win the COVID-19 challenge at the end of June. Modest goals. I think from the other teams on there, we have a very good shot. We have a good program plan. We just had a review with Zymetica. Suffice it to say, I thought it went really well. We're aiming to have a full function spec compliant ventilator by the end of June, and really start to then kick up to the next stage of manufacturing and delivering on that goal. Manufacturing discussions with Guatemalan Indian partners in a U.S. nonprofit. We're not just planning to put this thing on the internet. We want to see this thing through to completion. Okay, so that's sort of the background. We're really going to focus on the hardware. We're going to focus on the system implementation today. So that was sort of all of the big picture stuff, but really want to talk about how what we've learned over the last month has influenced the controls and how that's influenced the mechanical implementation because of how that's going to affect everything. But just like kind of high level updates. So we're aiming for a final cost less than $2,500. That's after labor, delivery, etc. That means we really need to target a BOM cost of like somewhere south of $1,000 to $1,200. I think that's sort of from where there exist markets where the marginal cost to avoiding that ICU bed is really the ventilator and not the staff or the paralytics or whatever. So that's really the cost where we can start to see ICU beds with ventilators where there really weren't before, or stocking up for mass casualty events, or stocking up for pandemic response supplies. Licensing regulation, we're not currently targeting an EUA, but potentially we are. I think we need to figure out what the fastest path to market is and whether that's going with a country's kind of independent EUA or the US EUA. The US EUA is an interesting and evolving thing, and as the pandemic has evolved, that process has changed a little bit, or seems to have from the outside. So we need to understand exactly what the cost trade-off is there, but right now that's like not our current target because we're not targeting a US deployment. Partners, so as mentioned on the last stage, we have ongoing discussions with 3 partners, and really manufacturing ourselves is also not out of the question. So there's a lot of things in flux with like our long-term strategic view, but for all of them, the next step is getting to a prototype that meets the performance requirements. And so like regardless of where any of those diverging branches go, we need a prototype that meets the performance requirements, and that's on the path to all of them. So okay. So design review topics. First, we're going to go through the updated pneumatic system review just to get everyone on the same page of like what's changed and what's new there and why. We're going to go through the pneumatic concept of operations, the air control, O2 control, and the exhaust control, kind of what's happening in those cycles. We're going to talk about the expiratory pinch valve that a lot of work has been going on, and then update on the blower response time issue that was sort of high on mind at PDR. We're going to talk about some of the issues and developments with flow measurement, the controller status, patient filtration connections, power supply, case design, and UI integration. If there was anything that I missed, any big topics we need to discuss, feel free to throw those in the chat or on the Slack, which I will, I guess, look at. Cool. So hardware requirements, we're in the process of moving to ValSpace. I know, there's been a bunch of people working on requirements. I think, maybe we talked in the Monday meeting about kind of the true status there. There's a lot of stuff kind of shifting around. I think the consensus is that we're going to move into ValSpace. We're definitely learning it's not a perfect tool. I think it's markedly better than Excel. If you guys don't know, there is a rw/ValSpace Slack channel where we can talk to ValSpace directly, as well as our requirements channel internally. There's a public login, so you don't need to create an account. Anyone can use those public credentials to just log in and see requirements, which I think is pretty cool. So you can find that information pinned over in the requirements Slack channel. And then as well, from the top level requirements index, I think if there isn't, there's gonna be pointers to some of this new information. So I know requirements have been in flux for a while. And I know that, that's kind of a thing that's really annoying to deal with while you're doing an engineering project. It's nice to just get given, here's all the requirements and then go meet them. This is obviously a requirements development exercise in parallel to an engineering exercise. So it's definitely a frustrating place to be, but thanks everyone for your patience. And thank you so much to everyone who I won't even try to name because I don't know who's been doing what, but I know a number of the team has been spending a ton of time working on that. So thank you.
I will say that like what we are trying to do is virtually unheard of. Like the amount of parallel developing and this development and the speed at which we're trying to do things is absolutely incredible. Like I've been at some really crazy places, some really crazy engineering efforts, and I think this tops them. So way to go. And
As
if
a
it seems
volunteer
hard
effort.
sometimes, that's because it is.
Yeah, it's just I mean, a pretty good group, and it'd be cool to think what we could do if all of us had full time to work on this. Anyway, so in terms of getting to coordination, updated the system functional block diagram. This is, definitely a work in progress and open to feedback on it. The objective here is to make something static that will last beyond design revisions. So there's some stuff that isn't necessarily hard coded in that seems like it might change, but in general, I was trying to create a framework for the major interfaces that we need to keep track of and the major subsystems we need to keep track of. Hopefully, as the engineering effort goes and we understand the system a little better, we can break these down and start to part them off so that we can fix the interfaces for each and maybe start to take advantage more of the parallel development network. But just briefly walking people through it, starting from kind of the external hospital environment. We have the intake air filter, the air control module, which is my systems engineering speak for the combination of the fan/blower and the air control valve. So that's really what's controlling the air pressure and flow rate. And that's going into a mixing chamber, which might just be a T, which is in the current design. And I'll talk through the pneumatics in the next slide. But then we also have the O2 interface, which is the O2 control module, which is going to do the same thing with the compressed O2. We're going to have a sensing module to get FiO2, as well as a flow measurement subsystem, pressure relief subsystem, and then a tubing filter interface to the patient. And on the expiratory limb, we're still planning to have this internal to the device. Obviously, this is one of the open questions we'll talk about later, but in the interim, patient airway pressure monitoring, flow monitoring, and then exhale control module. So yeah, and then out to the exhaust filter back to the hospital environment. Yep. Okay. So moving on to the pneumatics overview, which is talking, basically it's parallel to this slide, but a little bit more implementation focused. So this is sort of a current like chalk line snap of the pneumatics. So we have the O2 supply line from the hospital. We may or may not have a regulator, or we have the pinch valve we're going to talk about. That comes into the mixing chamber. We have the air intake going into the fan. That also goes into the mixing chamber. There's this bypass line, which we're still working on the exact implementation. And I know John has been doing some modeling to try and figure out what resistance that bypass leg needs to have and which side of the valve it should go on. But that's really there just to protect the fan from its own dynamics and prevent fan surge and fan stall. So that's somewhere between 0 and a fairly small amount of flow, and really just about protecting the fan. From there, those two lines mix, go past the O2 sensor, which we'll talk about, go through the inhale flow measurement, overpressure relief to the patient. We've moved the humidifier external to the design. So I think some of the feedback we got was that mostly the humidifiers are standalone units. I think we're not planning on, and maybe this needs to update in the PCB, even having the heater control. So I think we were talking about having the heater potentially be powered by the ventilator, but have everything else be standalone. I think that's still something that we should nail down on. I think it's just not like as big of a priority as some of the other stuff.
Yeah, I think it's good to leave it as an option, but not to spend a lot of time on it.
Yep. Yeah, and at this point, like taking it out, doesn't save a lot of cost and adds time. So it's still in there. And then coming back on the expiratory limb, these are again in the box. The patient side filtration, patient flow measurement, check valve, and then the exhale proportional valve. Does anyone have any questions? Just like, I know that was kind of quick, and I know not everyone has necessarily seen this before. I just want to pause briefly. You can either throw in the chat or unmute. If anyone wants to, yeah, go ahead, Neil.
I had a quick question. The one-way valves, are those things we have?
Sort of, no. We had one-way valves that work for here, and the one-way valve here is pretty cheap. If we need a one-way valve here, that's something we still need to research because the one we have is a pretty high cracking pressure. And then the one we have here, we still need to investigate it if it works. It has a high cracking pressure, which is fine because the fan can generate that, but it puts some extra burden on the fan and it's not clear how that's going to affect dynamics. So ideally, we would find a lower pressure one-way valve. There's in the issue for this, I updated with the duckbill valve that Mohan sent us. So.
Ethan, I'm going to pass along a comment from the hardware PDR. Grace says, it would be helpful to hear a quick summary of the purpose of the different parts rather than just the name of the component for us folks who aren't in the thick of hardware dev.
Sure. Yeah, actually, I think to do that even like functionally, and part of the reason why I just kind of clicked through it is now we're going to talk through like the state actions that are happening for each of these cycles. So what each of the components are doing during each cycle. Because I think Dave did a really helpful job of making kind of a diagram and putting these slides together. So Dave, if you want to talk through it, I think you're still there, or I can do it.
Either way.
I'll just go because I'm already talking. So, so the first slide, we're going to talk about the inhale state. So just states and modes for a second. Modes are, I'm going to use that term to talk about like the different control modes. So the bypass leg orifice is probably shouldn't be on there. It's just saying that we may even add an additional restriction there. So it's just treating the leg as a resistance, and it's just saying tunable essentially there to allow different pressure flow relationships. Okay, so modes, it's SINV, assist control, like basically how is the ventilator as a whole functioning, versus states, I'm talking more like instantaneously what's happening, what's happening during inhale, what's happening during exhale. Yeah, so just like in terms of terminology. Okay, so for inhale, what's happening? For inhale, we need to increase the patient pressure. So we're going to do that by increasing the flow of gases. Right now, with the split of the oxygen from the air, which we're going to talk about later, both of those valves are essentially going to move together, and those are going to be closed loop control on pressure. So each of these valves, which we'll talk about the actual mechanical implementation later, is controlling essentially the flow of air or oxygen. So right now, the baseline assumption is that the fan is running open. The fan's just basically on or hitting a set point, and maybe that loop point changes, but there's no feedback in there. It's just on. And same with the wall oxygen pressure is just on. And assumed to be fairly consistent, at least over seconds or tens of seconds. So then both of these valves swing together, right? So to open up, if we want to mix air and oxygen, both valves are going to open a little bit, and that's going to let air flow in. The fan, at some point, this valve might be closed, especially if we're at 100% oxygen. So if this valve is totally closed, then we just want some place for the air to escape, so you're not just running the fan against deadhead. Those two flows are going to mix in the piping. Essentially, we don't have an additional oxygen blender or anything to get finer mixing. And then that's going to go through the venturi, which is what is going to return flow. It's going to go past the overpressure relief valve, which is essentially preventing the patient from seeing pressure above a certain point. It's going to go through all the piping, get to the patient. We still haven't measured pressure, right? Just explaining that. So then all this, the pressure that's generated here that's not being measured is going to the patient. And then also that pressure kind of propagates through this piping into the flow measurement section. That's where we pick up pressure. So there's an issue there in that there's a difference in the pressure that's generated here and where it's controlled here. There's both a physical and time lag. The time lag is really small, but the physical lag is actually somewhat significant in the sense that there's pressure loss on this piping. But that's what goes to the patient. And then during inhale, this control valve, right, when this was a solenoid, this was just bang, closed, and 100% closed. With the pinch valve, there might be some leakage, which just establishes the bias flow to ensure that flow always is going one way through the ventilator and nothing ever comes back through the wrong leg. But with this very small leakage here, we're able to build up pressure really rapidly, and that's what drives flow into the patient. Yeah. Grace, is this like sort of answering your question? Cool. Okay, so then it's time to exhale. When it's time to exhale, we're going to close the oxygen valve. We don't need to be wasting any oxygen during exhale. And then we're going to open the exhale valve. We might not open it like all the way, right? We might open it, or we might not just treat it like a solenoid and jump it to full open. We might jump it to full open and then ramp it slowly closed as we assume the patient's exhaling. Or we could run closed loop control where this is the valve that's like controlling patient pressure and closing as the patient exhale ends. Right now, we're going to try and maintain closed loop control just on this one valve to try and simplify the dynamics, but that's like definitely up in the air, and we need to play with it. And John, that's something that would be great to get feedback from the system model on. Is that what it's called, model on? But so what happens during what happens during exhale is we close the oxygen valve to keep the flow loss down. The fan, right, is open loop control. It's still just kind of running, and maybe we turn it down briefly or turn it down slightly, but we modulate the pressure. So we need to establish PEEP during exhale. So to establish PEEP while the patient exhale rate is changing, we're building resistance against this valve. So all the flow is going out and dropping pressure as it runs against this restriction. And the amount of flow is proportional to the pressure drop. The pressure drop is what's seen by the patient. So if we're trying to maintain a PEEP of 20 centimeters, we need enough flow going through this partially open valve to establish that PEEP. And that's something that we'll have to talk through between the controller and the physical implementation and how that actually gets put in place. But that's sort of the theory, that we're going to let it leak and just push more flow through it. So let's say the patient is breathing out at 60 liters a minute, and it's going through this slightly closed valve, and we actually need 80 liters a minute to establish our PEEP. So then this valve is going to open until we're getting 40 liters of flow through. We're not actually going to measure that based on flow. We're just going to let the flow work out based on the pressure we're trying to hit. How much sense did that make to people? Close enough? Anyone want me to try that again? Okay, I'm gonna keep going. Okay, so then oxygen control is it's an independent state, but it's really related there. And I think to do that, I'm gonna skip the pneumatic slide and talk through these like representative data or representative figures essentially. So coming back to here for a second, we're going to treat the oxygen and the air valve as one valve during inhale. So assuming that they were perfectly linear and running off the same pressure source, then it would be exactly proportional, but they're going to be at different pressures and different valves with different characteristics. So we're going to have to apply some correction to essentially get them to be linear and proportional. But what that means is just like taking the two extremes, 100% FiO2, only this valve is open, and we're going to close loop control this valve position to get the patient pressure that we're trying to hit, essentially, right? Everything we do is pressure controlled. To get 21% FiO2 or 100% air, this valve is going to stay fully closed, and we're going to close loop control this valve to get the pressure we're trying to hit. At any point in between, we're going to add those two modes together, but we're not going to try and control FiO2 at the same time as we're controlling pressure. So what we're going to do is we're going to establish a proportionality rate, right? Let's say our target FiO2 is 40%. And I'm going to talk about air and oxygen mixtures because it makes the math easier. Or actually, never mind. Let's say our target FiO2 is 60%, which works out to 50-50 air and oxygen. So at 60% FiO2, we're going to open both of these valves equally in parallel, right? And as those valves need to adjust pressure, they're going to move together. So if our controller says, hey, pressure's a little low, both of those valves are going to open 50% as much as they would if it was like the 100% case. So what that looks like, from a data context is this, make that go away. Let's say the pink line is the oxygen valve state, and the blue dashed line is the air valve state. So for FiO2 of 0.6, they're both going to open and close together. Now, what they do during exhale is going to be different to try and conserve oxygen. In FiO2 of 100%, the pink valve is going to open fully, and the oxygen valve is going to open fully, the air valve is going to close fully. But so I just want to like emphasize the point that we're not controlling O2 rate during the breath. So we're not going to say, hey, not only is pressure low, but the O2 like concentration is also low, right? We're going to try and simplify the system dynamics, we're going to try and do this as an adaptive control over multiple breaths. So it might take 3 or 4 breaths for that proportionality rate to converge on a value that hits the FiO2 target. So if we're trying to get to 60% FiO2, we're going to have a guess value of how much both of these valves need to swing open to get to 50-50. And then we're going to average out the O2 over the breath and say, hey, FiO2 was targeting 60, but it came out to 55%. 55% isn't what we wanted, so we're going to switch that ratio a little bit to have the O2 valve open a little bit more proportional with the oxygen or with the air valve. Does that make sense? Mohan, feel free to like unmute too if you're trying to.
Yeah, I just had a comment here. So you're using a galvanic cell for the O2 sensor, right?
For now.
Okay, so just for historical context, in other ventilators, the O2 sensor is almost never used as part of a closed loop or long-term adaptive strategy. It's just used as a monitor only. I'm not sure what the reason is, but it might have to do with the fact that they wear out. They typically last about 12 months before you have to replace the O2 sensor, and so they're typically not used as part of any control routines.
Yeah, that's one of the reasons we're trying to pursue a fluorescence quenching cell, which doesn't have a limited lifetime the same way as the electrochemical ones. The difficulty with that is just trying to find a supplier that has can supply a steady chain of them.
Yeah, I've looked at those. I couldn't find one that goes above like 30% O2.
Yeah, I have one here, and it works. It works really well. It's just a question of being able to get them. I have one in a rebreather that I use here.
Can it measure up to 100% O2?
Yeah.
Oh, really? Okay.
Yep. Yeah. Tested and working. It just we don't know that we can actually get them.
I
can post the part number for that.
Yeah, I'd be interested to take a look at that.
So open question. I think there's still some open question on how we do O2 sensing. So that's good feedback. And then I know other options are going with a flow sensor on the oxygen line. One of the feedbacks that pushed us this way was not being certain about what the actual O2 concentration is in the O2 line. And so if you don't know what the O2 concentration if the people that filled your tank said it was 100% O2, but it's actually 80% O2, you want to be able to provide that feedback to the doctor that even in 100% setting, you're not getting 100% FiO2. Yeah. And then to echo Edwin's point, the chat here is going to disappear. So really try and only use the chat if you're not in our Slack. And if you'd like to be in our Slack, feel free to message Edwin and we could probably add you there.
Yeah, I think Justin sent out a sign yourself up link. So
sweet.
Folks, if you want to be on our Slack, go grab that just a little bit higher up in the Zoom chat there. There's a link to add yourself on Slack.
Awesome.
Just so y'all know, if there are ever future large group meetings, there is a way in the Zoom admin to disable chat if we always want to, like, in the future.
Yeah, cool. Okay, so that's kind of the end of the system level control strategy. Since it's kind of a shift, right? We've added some complications from the solenoid and the fan. Just wanted to pause there. I saw there was a couple questions in the Slack and in the group chat. Anyone have any other questions about like why we're doing that or what might change? And then just also to pitch, Dave Gerson has been working on a ConOps that kind of types out some of that stuff. So not sure if that's posted any channels yet, but I'm sure he could, as a result of this call, post that somewhere.
I have a question regarding the sort of the control design. I mean, not really the control design, just the hardware part of it. So I know this is very strongly a pressure control, based system right now, and at least some physicians are like concerned about having volume-based inputs, and I wonder if this architecture would be able to accommodate that without any changes. Rather, it's a matter of software control.
I think eventually, once we get to the reason we're pursuing a pressure-based control is we have lingering issues with flow measurement, and we're not doing a fixed volume method. So we have to essentially sense flow to get volume, and we're less confident in that than our ability to sense pressure. So we are targeting pressure control modes with and without like volume-based adaptation, with the impression that we just have better control of pressure than volume. Hopefully, like as we get some of the sensor issues worked out and narrow down on a control strategy there, we'll be able to like just have implementation in software with the same architecture to a volume-based mode. It's just, it's better, especially now while we're like working early in the system, to have the control strategy closed around the pressure that we're like measuring directly rather than the twice integrated volume measurement.
Do you think that is a function of the sensor type that we have chosen, or do you think that's something that can be iterated upon in like sort of?
I think we intend to get that flow measurement to the point where we can do volume integration. Whether that has to mean changing sensors is actually going to be a whole topic coming up later in the design review. So I'm going to keep moving.
Okay, thanks.
We'll come back to there.
That's it.
Anything else? Cool. Cool. Well, so update. We talked about in PDR was the solenoid sourcing for the solenoids, the design requirements for the solenoids. There was that was kind of one issue. We looked at solenoids from Burkert. We looked at solenoids from US Solid. Couldn't really find anything that made sense, and it was really just because like it was a weird application for the solenoids that we could buy off the shelf that weren't part replacements out of ventilators. So Mark has taken the lead on putting together this pinch valve, but also has had a ton of help from Steve and Edwin and other people who I'm probably forgetting. And I think we've really gotten to a concept that demonstrates that the pinch valve concept, or at least some proportional, controlled valve, is able to affect the control that we need to here and be significantly cheaper than the solenoids. So I think this basically is the answer to that question we raised in PDR of what do we do with the expiratory valve. And so Mark, I mean, if you want to talk about it at all, otherwise I'm happy to.
The idea here is just going for a simple design that uses a motor that we know is good for the cycles and tube intended for a peristaltic pump that's good for cycles. It's really just kind of an exercise in simplest ways of doing things. And as of Edwin's most recent round of testing with a more powerful stepper, it looks like it's valid. So it sounds like the IAV is still probably a preferable choice if it is adequate, if it works with oxygen. But this is a backup design that seems to be a valid choice.
Yeah, and I think
I will say, actually, I think it's more than a backup design. It's primary until we prove that the IAV can work. I think the IAV has some nice features to it, and that it's lighter weight and cheaper to implement. But until we know that that can actually be used for this application, I still consider the pinch valve to be a primary.
Mark, can I ask you, have you characterized the response of the tubing to the release of pinch? Like how quickly does that respond?
Edwin's been doing the bench work here.
Yeah, I just posted some data very late last night, so most people probably haven't had a chance to see it. But in the issue ticket on, I think it's issue number 5, the blower response time, I did some measurement with that, and the response time is very fast. It's on the order of 200 milliseconds for recovery. So there is some hysteresis, right, that it closes faster than it opens, but only by a bit.
Okay, thanks.
And then as well, if you guys, well, we probably need to do this either way. And Edwin, I'm not sure what you have set up to do it, so we could either talk you through it or not. But at least I'd started to talk to Brian about building a valve characterization stand up in the port to get flow and pressure curves for the valves at their different operating characteristics, and maybe we could also try and get some dynamics of that. I think you have a handle on the dynamics right now, so.
Yeah, I think we have a lot of use for like a flow volume characterization stand would be useful for a lot of reasons.
Yeah. So
Awesome.
that's on my docket for this week. Cool. So I think the really important thing here is that once we kind of started going down this path, we realized this could solve, or at least address some of our blower response time issues. And whether or not this is the exact right valve, I think it gives us the architecture flexibility to say, hey, the world's engineering can come up with something here, even if this isn't perfect, but it gives us the ability to kind of move the rest of the system forward and come back and replace this later if we ever need to make changes. And so this kind of gives us the confidence to lock the architecture down and move forward. So, as Edwin and Mark talked about, one of the other major issues coming out of PDR was the blower response time. So on the bottom right, we have a sim result from John up at Medelica land. And this was potentially even faster than some of the responses that we were seeing with the physical model. And this isn't a very aggressive test. And what you basically are seeing is that the command pressure was up at like 24 centimeters. And during that breath time, the pressure wasn't getting anywhere close. And this, it really isn't an artifact of simulation. We validated this with both, some of the breadboard models as well as the integration model. And it really just like that fan just at 12 volts couldn't put enough power through it to accelerate flow that quickly. And so we looked at a bunch of different fans and looked at the supply chain for them and more or less came to the conclusion that ramping the fan was going to be a harder problem than adding a valve after the fan. So that's what we decided to do. And in this, as talked about in the previous slides, the fan here is going to run open loop. So the pressure is controlled by the valve position and the fan runs open loop. We could theoretically get a faster response by running both of them closed loop, but then you get into a significantly trickier, dynamics controls problem that we didn't want to tackle right now. So that's potential, down the line architecture to explore. But right now we're going to try and keep things simple to keep things from breaking. But so, generally we've settled on putting a valve after the fan that allows us to use much more available fans. But it means that we need to settle on the valve. So Edwin has done a bunch of testing with an IAV, which is out of a car engine. It's a stepper motor in a body that we can interface with the tubing, and has been pretty good. The issues with it are mainly concerns around oxygen, which isn't as much of an issue in the one directly after the blower, but it is an issue on exhale potentially, and certainly is an issue on the oxygen line. As kind of Mark and Edwin were talking about before, it's potentially the leading candidate, but we really need to make sure it works. And then there's some concern on the supply chain for putting these things into a medical device and whether that would really pose a hurdle. I think, biases, we'll see. The pinch valve definitely gives us the option of saying, we know we have something that works, and better is better than not having an answer at all. So hopefully we can work on better, but we have an answer.
Yeah, and I think the really important answer that we got was that we can achieve the response time we need using some kind of a proportional valve combined with the blower, and that we don't need to try and pursue a higher performance blower, which we're having trouble getting a supply chain set up for.
So speaking of performance, some of the freshest pizza results from Edwin's kitchen last night, 3:34 a.m. Edwin, man, you've been a force. But so this is an awesome closed loop pressure tracking on the pinch valve with the fan. So I'd love to see these be higher pips and peeps and a faster rate. But I think preliminary rise time, tau of 220 milliseconds is pretty good. So yeah, I think let's see where we can go there. But it's definitely much more promising than where we were at the end of PDR. I think that's kind of summarizing what I just said. This is mainly just the comment again that we could shift to control, we could either open loop control the valve or the fan, or both, or closed loop control both. And I think right now we're going to aim around closed loop control the valve. Edwin, did you have any comments or thoughts on that?
Yeah, so this is essentially just a skeleton concept of operations for the blower control. We know that we won't need the blower to respond instantaneously, right? It's no longer critical for the real-time pressure control of the breathing loop. However, there's still some performance that we can gain by controlling the blower. So what I propose here is that we have the system watch the sort of the operating envelope of the pinch valve, or whichever proportional valve we use. It watches that operational envelope, and it keeps that envelope within the most effective dynamic range of the actuator, right? So we can sort of slide that back and forth in a slower loop than the pressure response loop, which is the main real-time control of the ventilator. So that's something we can look at, and I think it's not something that we need to focus on right now, but it is a place where it's another knob that we can turn to gain additional performance.
Awesome.
And it might also be good for, say, reducing oxygen waste during PEEP exhale.
So I also just, thanks to whoever on the chat, I missed that. I think it was Elizabeth and Martin. You know, as we're a pretty open team, this is gonna be a slight tangent, but I'll bring it back really quickly. As we're, you know, a pretty open team and we're changing anything we do in our communication and language to like facilitate having a collaborative team is really important. So I think avoiding abbreviations is one of the things that we should do there. So IAV is probably a bad abbreviation also, because it's abbreviating idle air control valve as IAV. So if you were Googling what IAV was, you could have Googled IAC and found something. IAV probably won't return anything, but you know, trying to settle on like air valve or air control valve. You know, I know, especially when you're repeating the same 3-word phrase a lot of times, and especially if you have an aerospace background, it's really easy to just, I'll just like crunch those together.
The TLA trap, 3-letter
dreaded
acronym.
TLA, but yeah, especially as a team, we can try and.
Yeah, I'll give a quick background on that then. I think perhaps a better term for the IAV would be a stepper-driven pintle valve. So essentially, what it is it's a cone-shaped plunger that goes in. So you imagine you have a cylindrical orifice, right? A pipe through which flow is going, and then you have a cone-shaped plunger, which then goes into that pipe, and it basically, as the diameter changes as it enters the pipe, it creates a variable-sized orifice. So it is essentially a variable resistance on the flow that's coming through that pipe. So perhaps we can call it the stepper-driven pintle.
Yeah, I was
trying not to snicker.
I think, yeah, blower control valve or air control valve. Let's settle on term, but I think IAV probably should go away.
That's a good call out. Thanks, guys.
Cool. Okay, so O2 control we talked about a little bit. We had been really hoping, and I can't say we've like fully explored this to death, and it is simple. We've been really hoping that just running the oxygen as a manual valve that has, you know, a constant flow rate and using the fan to mix in air or control that would allow us to eliminate an oxygen control valve. I just have become very skeptical. I don't know what of the actual simulation results we've done to really validate that it's infeasible, but one of the things we, you know, had looked into was like the time averaging of the oxygen mixture. So doing 100% O2 at the beginning of the breath and 21% O2 at the end isn't really the same thing as delivering that oxygen consistently over the breath. And so that really does drive us towards an oxygen control valve that's able to proportionally control the flow rate from the oxygen. So everything we've done for air control, we pretty much need to do in parallel for the oxygen control, because at 100% FiO2, you know, there is no air, the fan's not really doing anything. So current baseline is separate air and O2 and a separate lens and mix. We could have the O2 come in upstream of the fan, but there's a number of concerns around that. So mainly it goes to the mixing and how we do the mixing, and then the fan compliance. So the mixing really has to do with that averaging issue I talked about a second ago, and that a lot of the kind of passive oxygen mixing schemes would only ever deliver like an average amount of oxygen rather than kind of a consistent amount of oxygen. So it's like 50% for half the time and 0% for half the time isn't the same thing as 30% or 25% for the whole time. But then the other real issue is blowing, you know, oxygen through the fan has an issue with like fan sourcing. And, you know, we've asked the question, like, why is this so hard to blow atmospheric pressure oxygen through a fan? We did have a conversation with Moog, who's one of the potential blower suppliers, and they basically said, no way, no how, you cannot blow pure oxygen through the fan at atmospheric pressure. They were concerned about sparks and fire safety mainly. So we have found fans that are 100% O2 rated. This is a thing that's used in ventilators. It would simplify some of the controls, but it seems to significantly complicate the fan sourcing. We still need an oxygen control valve in that context. So I think, for now, the baseline is to separately control the oxygen from the air and have check valves to prevent the oxygen from going back up into the air, into the fan. Okay, so flow measurement was a pretty unresolved question at PDR. It is now a more resolved question, but still a very open question. So we've settled on a Venturi as the flow measurement solution. Here you can see a pretty cool light box view of one of our Venturis, seeing the internal geometry. Thanks 3D printing, this is from Polyspectra. And side note, if anyone's doing dev and needs Venturis, I have a stack of Venturis now on my desk. I'm happy to tap them and order the barb fittings and send them to anyone who needs for a dev build. So feel free to hit me up in the dev hardware channel. So Venturis provide a high signal to DP ratio, which allows us to use very cheap differential pressure sensors, but they're highly nonlinear. We've done some calibration. So Chuck Tung tested a physical instrument within 1% accuracy at 60 liters a minute using a spirometer. We'll be able to validate those better as we improve our flow calibration stands. Brian and I also did a volume integration calibration where we inflated a bag at 8 liters a minute. And within our resolution, the ability to measure the volume of the bag, we got the same answer. We also tried blowing through it, which seemed to have at least the right profile for the flow rate. So it seems good for flow, but the question is it really good enough for volume, which is more challenging since you're differencing flow across 2 sensors and integrating that difference. So far the answer is possibly not. The flow measurement channel has had some pretty long threads about this, but the main issue is the way the sensors work is there's a offset. That offset is very temperature dependent. It's a strain gauge measuring pressure. And so, when we have 2 differential pressure sensors, even at 0 flow rate, you can see the average, or the difference integral wandering. And if this was like a straight line, that would be great, right? If it was a straight line, we say, hey, this is a consistent straight line. We just subtract 2 liters a minute from one to the other, and we get perfectly 0. The problem is it changes, and it can change like pretty quickly, even over the course of seconds. Like with your finger, you can drive it to be flat. But if the patient's breathing and volume's also changing, it's really hard to cancel out that integral without, enforcing volume compliance. So, whether the issue is a better pressure sensor or a redundant pressure sensor, differential pressure sensors, or a different, flow measurement solution in general, that's still something we need to work out pretty quickly. And Steve has had some thoughts about this as well, temperature compensating them to make sure that they're at the exact same temperature. Yeah, that's still an open question, but really the issue is the very, very small difference, right? You can see that the flow is basically 0, but it's biased below 0. And it's very hard to account for that offset, even some of the, yeah. I don't know, Justin, if you want to comment a little more. You've looked at this data more than anyone else.
I don't. I think you made a really good summary, but just for everybody who's looking at this data is with the blower off. And that's why it's concerning that we see this drift, especially we see this drift to 0 LPM. So that's how I've been doing a lot of these experiments. But when you turn the blower on, you do see the volume graph, which is this yellow line moving. But it's like the bumps from inflating the lung are not huge compared to this drift. So that's all.
Yep.
I will mention that I had a very good call with Randy Steck from LifeMech. And the ventilator they're building, they've had really good results with the thermal mass flow or the mass flow MEM sensors. And so he put a good vote in for them with great precision and stability. So
yeah, Randy. We've been using
Hey,
the
there is.
unit. I sent Edwin the details on it. We found some really good results, very, very close to lab measurements.
Which model are you using?
Randy?
I think you might be on mute microphone there. We looked at it. We did early on in this project too, look at a few of the mass flow sensors as well. And we originally decided to go away from them because of the cost and possible supply issues, but it might be worth taking a look at them again.
Yeah, hey Mohan, and you had said you had a contact with someone who potentially has thermal flow sensors. Anything happen with that? We're still interested. So
Yeah,
free to follow up.
for our project, we've managed to source a couple dozen of them. And yeah, I have contacts with a couple of the thermal flow sensor companies that I can introduce you to.
Cool, that'd be great.
Yeah, I think if it's something we really need, then it's something that we should pursue. We're still trying, putting a lot of effort into trying to make these cheap automotive DP sensors work. And I think that if we can, like if it does prove to be an actual solution, it'll be a huge boon because, these things cost a few dollars and they're available in the tens of thousands. But
Right.
if we need something else.
Yeah.
For your DP sensors using the NXP?
Yeah, that's what we have right now.
5004 DP.
And the main problem is offset drift?
Seems to be.
Seems to be, yeah.
One of the things that seemed interesting was potentially using two of them with the hope that the offset drift wouldn't be consistent.
Yeah, I haven't seen that before. What I've seen in a lot of older ventilators is they have an auto zeroing valve where they pneumatically short the two. Periodically, they short the two inputs together and they measure the offset. That happens either every breath or every couple minutes, something like that.
Electrically or pneumatically?
Pneumatically.
Huh.
Oh, every breath. I would really love to learn more about that. If we did it every breath, that would be something.
Yeah, we could potentially do that. Well, let's think about that.
Yeah. I mean, you need just a very small valve to pneumatically short those two together, right? So,
Yeah.
on the expiratory cycle, you could auto zero the inspiratory sensor, right? And on the inspiratory cycle, auto zero the other sensor, something like that.
Interesting. So moving through just to try and kind of keep, we have a half hour left. So it's actually, I think we're actually at a good pace. But keep moving and then, save some time for discussion after. So the main thing on kind of the system kind of control architecture is that we moved from an Arduino to STM32. I think everything else is fairly consistent and we've added the proportional valves. And then Edwin, for anyone who wasn't at the kind of PDR, do you want to just give a high level, like 30-second on the controller architecture, the split between the RPi and the STM32?
Yeah, certainly. Do you want to just click back to the last slide there?
Yeah,
I'll talk about it from there.
It's doing its own thing.
It's trying. Yeah, there we go. Cool, thanks. So early on in the design, we essentially decided to split the UI computer, which you see at the top in the purple here, the user interface computer with the real-time control microcontroller, which is actually doing the sensing and controlling the respiratory cycle. And the reason for doing that is we wanted to minimize the amount of code that needed to be scrutinized for real-time control. So what that opens up for us is to be able to use Linux and a full UI on the display computer while keeping the computer that does the fast response control fairly relatively simple. And I think that we pursued this to make our certification easier and also to decouple those two computers. And so we don't really have to worry about what the UI might be doing in the background, which might change the response time of the pressure control loop. The other reason for doing this is that there's a fairly significant separation in the response time of each of these systems. So up at the top, you see the user interface response time. So this is the response time of a clinician caretaker, like interacting with the unit and updating it for the patient's condition, all the way down to the patient's actual physical response, right? Lungs inflating and deflating, which is physics, right? So this happens immediately. And the kind of a way to look at this architecture is by looking at how the response times stack up. So you have the patient, which operates in real time, and then the pneumatic circuit, which responds in the millisecond range, and then the electronics themselves, right? The actual sensors will respond on sort of the tens of milliseconds ranges, and so the controller needs to do the same. So the control unit, which is the STM32 now, responds in the 1/100th of a second response rate, and the UI computer responds in the 1 to 60 seconds range. So it's sort of like breath to breath time range. And then there are information that are passed at different resolutions between each of these systems. Yeah. Any questions on that? I think this is relatively unchanged from the original PDR that we had last.
Cool. Yeah, I mean, you want to just keep going, Edwin, on some of the electrical design updates?
Yep. The main difference from last time, the main bit of progress is that we've now moved to this custom circuit board. So we had sort of a breadboard set up with a few different dev boards that are kind of hooked together with the racinets of cables on people's desks. And now we have something more formal and closer to what we expect to have in the final ventilator. And some of the major changes, the biggest one, of course, is that we've moved from Arduino to STM32, which gives us more memory, more speed, and a floating point unit for doing mathematical calculations that are required for the control. And one of the things that also brings with it is more of an established tool chain that's used for other medical devices. So the Arduino tool chain is not really set up to do medical devices, and it's there are parts of it that are abstracted or obfuscated. And so going to the STM32 tool chain, I think, helps us in that regard. The controller to Pi serial connection is now fully baked into the board, so no more level translators and wires snaking around potentially high noise like motor connections and things like that. And there's a SD card has been added so that for debugging, we can log data from the cycle controller, whether or not we are piping data out to the UI. And the analog sensors now have real filtering. So we just had them directly connected before. There was no anti-aliasing there. So we have filtering on those sensors, which I think has improved our trust in our signals a bit more. And also this board, since we didn't know what our final sensing solution was going to be, this board also adds 4 I2C ports that can be individually addressed to allow us the option of communicating with digital sensors. Gives us something to experiment with if we go with other sensors. And then finally, this was kind of almost an kind of a hedge in the original design when we made the circuit board, was this option to add a stepper controller module on top of the STM32. And now that the proportional valve has become much more real, it's saving our bacon. So we also have the option to add the stepper module so that we can control stepper motors, up to 3 stepper motors from this board as well. So, yep, that's
good job being super on the ball on that, Edwin.
Yeah, well, that was also credit goes to Neil too for pushing for including the ability to add those stepper modules.
Sweet.
Yep, and if anybody needs this dev hardware, we've set up a dedicated Slack channel tagged dev hardware for people to request dev hardware and get support on the dev hardware for their own setups.
Edwin, what do you use for your IDE?
That is a question.
That.
Yes, thank you, Justin.
We do not have a standardized IDE. We have a standardized build system, which is called Platform IO, and then developers can use whatever text editors they wish.
Okay, thanks.
I did not understand that question.
Thanks, Justin.
Let alone the answer.
So yeah, any questions on that hardware, direct them to the dev hardware channel, including
and
requests
Martin,
to get hardware.
Yeah, there's
And Martin has also been working on an excellent set of documentation for using the dev hardware and building the pneumatic circuit and the accessories to go around it for more complete simulation.
Yep. So if you guys need
And that's all in Git.
If you guys need any hardware, need any help setting up the hardware, or want to buy stuff on your own and hook it up, there's a good documentation set, and we're happy to support you if it helps you guys do software development. Cool. So the next topic is the kind of shifting directions in terms of filtering, is the patient viral filtration. So Alpha had inlet exhaust filtration and then was totally kind of a closed loop to the patient. So that was really protecting the patient from what was in the air and protecting people from what was in the patient. But what it wasn't doing was protecting the ventilator, protecting potentially the transmission of disease from ventilator to or from patient to patient, through the ventilator, and then as well, keeping the internal environment of the ventilator from getting contaminated with whatever viruses or bacteria were in the lungs. That became an issue with a number of conversations on our medical review. And so we've moved towards a system. You can see the panel mount here in the bottom. So it's a 2-piece mold. Mark, happy to have you, or Elizabeth, whichever one of you guys wants to talk. I know you guys worked on this together, or thought you did.
Yeah. And also I wanted to just mention, I don't know if you guys are aware of CPAP filters. They're sort of pad-shaped filters, a little bit bigger than this, but flatter. I don't know if we're ruling those out for supply chain reasons, but they exist.
So the goal, that's sort of this last bullet point, was the idea of using that 22 millimeter taper means that you can, I think, use those filters still, if you don't want to use the filter.
These are different than that, though. These are just pads. These look like they're designed for home use, optimized for cheap, as opposed to hospital use, optimized for...
I have one.
Yeah, I think you're talking about the ones that are in like slide 3, right?
They're in my,
yeah, that one.
Oh, like that. Okay.
I'm learning about that now. So,
Fantastic. Can you post something about that if you haven't already in the Slack channel so we don't lose it?
Sure.
Awesome.
I think, so, well, just high level goal, the shift was basically enforcing that we need filtration on the patient side, not just on the kind of ventilator side. So not just on the hospital side over on the left, but also in between the patient and the ventilator. And so, the current design uses the Roomba filters in this removable panel mount. So you can replace those filters between patients to kind of make that filtration bridge between the patient air and the ventilator air. And then as well, I think using the same half of the filter to do the filtration for the air intake and the exhaust from the machine. Theoretically, if everything's going right, the fan exhaust shouldn't need filtration, but I think it seems like a good backup. I think one of the feedbacks we've gotten is just counting on staff to use those filters is not something that we can necessarily do. And then counting on those filters to be available is not something that we can necessarily do. And so, I think it's a compromise we came to of we are going to have to rely on the staff to do some work. And that's, that's a decision we made. It's a trade that has consequences either way. But that if they do that, then this architecture should work. And I know, there's some ongoing discussions around the expiratory limb location. I know, Mohan, you've been asking a lot of questions about that with Gradient. So I think for now, this is still going to be our go forward path to have these kind of 4 filters as part of the device. But we'll continue to revise as we learn more. I don't know, Mohan, if you wanted to comment on that.
I was just curious, were you going to recommend any filter replacement schedule, like for every patient or a certain number of hours, or what are your thoughts on that?
My thoughts, based not on any analysis yet, were that the surface area of those Roomba filters is like, or Mark, if you've done any of them.
Oh, stop it.
Don't let me speak over that.
the Roomba filters, the only point of reference I have in this is that they're, for vacuum purposes, supposed to be changed every 2 weeks. I've not run numbers in this.
But just from like a surface area perspective, it's like 10 times more surface area than the patient filters that are changed every day. So
yeah,
2 weeks does seem potentially feasible.
Yeah.
Have you looked into whether they're effective at blocking viral and bacterial transmission?
So it's not the same level of the like sub-micron bacterial transmission, but Elizabeth has been doing some research, and there are definitely some papers to suggest that HEPA is a very good level of filtration that some, very, very tiny viruses could get through, but the efficiency, at 0.3 microns is pretty good.
I mean, it's HEPA standard. Past that, we don't know, and we kind of can't know without doing our own lab work.
Okay.
So are any of those viruses that are more likely to pass through, are those, any of those, I think what we should look into is if any of those are associated with like not morbidities, but like illnesses that are likely to pop up with COVID or?
I mean, the point here is that this is the same level of viral filtration that any other thing that meets the HEPA standard is. And past that, we just don't know. But this, I don't think that this is a different particle range than anything else would be.
I think there are, the bacterial filters do go to a higher efficiency at that range. Elizabeth, I don't know if you want to summarize some of the research you were posting, if your audio works.
Yeah, sure. Again, we haven't finished doing like a full review of this, but what I've been reading so far is that that it's sort of most appropriate to analyze filters by a statistical method, and that a HEPA filter is rated for 0.3 micron particles. And the reason for that is that it is least efficient at removing 0.3 micron particles. So if things are smaller than that or much larger than that, they're more effective at removing those. So for 0.3 micron particles, HEPA filters have to be like 99.7% effective, meaning that like 0.3% of those particles will make it through on a single pass, but that effectiveness goes up for smaller particles, which the viruses that we're looking at typically are. And part of that has to do with like the dynamics of how the filter works. It's not just like a net that anything smaller passes through. The thinking is that that's true for particles that are bigger than that, but for particles that are smaller, they don't necessarily have enough inertia to make it through the filter. So like they can't hold enough momentum because they're smaller. But yeah, that's what we've been looking at. The other salient detail, which I was about to write in the chat, is that the resource that I found that from is from a manufacturer of patient isolation rooms. So like typically, if you were going to build an isolation room for not necessarily coronavirus, but like any other sort of infectious disease, the filtration for that environment goes through at least one layer of HEPA filtration. So that seems promising, at least.
As well, there was early on a NASA paper about HEPA filtration for COVID-19 that was pretty positive. And then Elizabeth also found some CDC guidance around using HEPA. So I think we've done as much research on this as we've done on anything. It seems to be that HEPA should be sufficient, given that it's a risk consequence curve, right? So, but if we learn something else, then we learn something else. I think it is. Yeah, there is a question of doing the filtration right at the patient, which we understood to be like an end user issue, but we are still counting on the end user to do things. So it's really around like being able to use more widely available filters, and we think we're adding benefit, and to use both kinds of filters. So it's maybe not like a totally consistent answer, because this does require it does require staff doing something to get it to work right. Kind of briefly, as we're kind of coming to the end, talking about battery supply. So we've been looking at power supply issues. I'll summarize this briefly, Edwin, but feel free to like throw a hand up, or anyone else who's been working on this if I say it wrong. So we're sticking with 12 volts. We explored 24 volts for a while and think we can make it work at 12 volt. And that really increases the availability of power supplies, and it increases the availability of backup power supplies, especially. So sticking with 12 volts standard through everything. we're not bringing mains power into the device, so we're going to use an external power supply. So we're not plugging AC into the wall, and that's again kind of going to standardization as well as safety. This gives people kind of flexible choice whether they use a large battery or UPC for backup power, or if the hospital is on backup power, then that's obviously another option. There's still
that's us falling into the TLA trap again. I think it's UPS for uninterruptible power supply.
Oh, there you go.
Yeah.
My bad. And then open question on an internal alarms battery. So whether we have a second, much smaller battery in the device that can't really run the ventilator, but is enough so that like if there is a power outage, the vent doesn't just go silent and dead. It goes dead and unhappy.
I think that's less of an open question anymore and moving more towards a necessity. That eventually, that's a discussion we should have in requirements. But I think that especially if we're relying on a fully external power supply, such that like tripping over the plug could pull it out, we will probably need to have some way of. It might even just be an ultra capacitor. It doesn't even need to be a battery, but it just needs to be able to make noise and complain if it's going to die.
Yep.
It is a requirement. So.
Oh, is it in the requirements already?
Yeah.
Rockin'. Thanks, guys.
Even better. And then it's too bad Elizabeth left because she's been thinking about case design. So obviously this is sort of on hold a little bit while we work through the internal mechanicals, but leaning towards a two-part folded metal case. We could still consider it a prefab case. There's plenty of case options that we could integrate with. Right now, going custom, just because it kind of gives us the full flexibility and doesn't add a ton of expense, and really kind of waiting to move this forward until pneumatic design. One thing that is important to note is that we're originally we're looking at the plastic, essentially tote bin as our case, based on some conversations with the supplier in Guatemala and like what they had available. But then I think that's sort of become our trademark, right? It's the open source design. Everything you see is what you get. You can look in and see what's going on. And so I think keeping a clear plastic panel on the case seems like an interesting trademark to kind of keep going forward with. So nothing huge to report there. It's still the alpha kind of internal mechanicals that are shown within beta. I know Elizabeth has started, I thought, a second build with some of the updated pneumatics. Okay, so I have a slide on next steps, but kind of wanted to pause on, if there's open questions we wanted to address, or whether we should run through these first. I guess I'll just do the last slide and then it can be like over. So we need to finalize and codify the performance requirements. We're currently, we have the requirements standard. We're informed by different ventilator specs and different challenge specs. We need to decide where we're going to make trades, and the ones that I'm most concerned about are some of the corner cases that Edwin was talking about, the high pip, high rate. If we think we can meet all of those, then great. But if we do need to trim some of those specifications on flow rate, on high pip PEEP, high respiratory rate, then that's something that we need to narrow down on and propagate through the rest of the requirements. We need to implement oxygen control. That's the next major functionality we really haven't demonstrated. I don't even know if it's been a focus of our modeling. I think it really hasn't been implemented too much in the simulation model. So that's really kind of the next major feature that we haven't even done proof of concept on. I think it's very similar to what we've been doing, so we have a lot of confidence, but it's definitely something that's sort of been untouched for a while. We need to move from the concept development on the air valves to reliability testing and characterization of them, kind of moving them from the ideation phase into implementation. As we kind of bring those components together, we're going to need to start worrying about EMC and electrical review for 60601 device qualification to make sure that it passes electrical review, and then start moving into manufacturing and maintenance design. We're not just building something once, we're building something that's going to last, that can be used. So, obviously designing in the manufacturability and maintainability is something that can't really be a full afterthought. So that's, I think, everything we have for slides. Thanks everyone for participating. And yeah, let's both go through any questions we have now and as well, keep things going in the hardware PDR Slack channel.
Absolutely awesome. Thanks for putting this all together, Ethan.
Yeah.
It's good to get everyone
Sure, so.
at the table to be on the same page with the design.
I'm gonna
Big
stop
ups,
the
not just to
recording.
Ethan, but also Edwin and Justin and Martin and just everyone who's been like busting their ass, like getting to this point.